A fully loaded jumbo jet hurtles down a fog-choked runway. The crew has no idea another aircraft is directly in their path. In seconds, 583 people will be dead. 5 crashes. 5 catastrophic failures, from fatal miscommunication to rogue software, that each forced the entire aviation industry to change. We're counting down the disasters that rewrote the rules of flight, starting with number 5. In 5th place, the Tenerife airport disaster stands as the deadliest accident in aviation history. On March 27, 1977, 2 fully loaded jumbo jets, one KLM 747 and one Pan Am 747, found themselves on a fog-bound runway at Los Rodeos Airport. Visibility dropped below 100 meters. The control tower, overwhelmed and working with only a single radio frequency, issued ambiguous instructions. The KLM captain, a respected chief instructor, believed he was cleared for takeoff. His first officer, hesitant to challenge, echoed the captain's assumption. Meanwhile, the Pan Am jet was still taxiing ahead, hidden in the dense fog. Overlapping radio transmissions masked the tower's words. The KLM crew heard only fragments. "We are at takeoff." "Okay." The final clearance was never explicitly received. At 160 knots, the KLM 747 thundered down the runway. The Pan Am captain spotted landing lights through the mist and shouted, "Get off! Get off!" But it was too late. The nose of the KLM jet tore through the Pan Am's fuselage, igniting a fireball. In less than a minute, 583 people lost their lives. The investigation revealed a lethal mix of unclear phraseology, cockpit hierarchy, and missing ground radar. The Spanish report concluded that the KLM captain's decision to take off without an explicit clearance was the primary cause, but it also pointed to systemic failures, ambiguous language, a lack of assertive communication, and infrastructure gaps. The aftermath forced the International Civil Aviation Organization to mandate unambiguous terms such as "cleared for takeoff," overhaul global air traffic control phraseology, and require crew resource management training in cockpits worldwide. Major airports installed surface movement radar, closing the gap that fog and confusion had exploited. The Tenerife tragedy proved that in aviation, a single misunderstood word can be fatal, and that clear communication is as vital as any piece of machinery. Number 4. Air France Flight 447 vanished into the Atlantic darkness, leaving behind only silence and questions. On June 1, 2009, the Airbus A330 was cruising at 35,000 feet when its pitot probes, exposed to supercooled ice crystals, began to freeze over. Within seconds, the autopilot disengaged. The cockpit filled with alarms and warnings. Airspeed indicators disagreed. The crew, faced with conflicting data, pulled the nose up, raising the angle of attack instead of pushing down to recover from the stall. For over 4 minutes, the aircraft descended in a deep stall, unnoticed by the pilots who fought against the very systems designed to protect them. All 228 people on board perished as the jet plunged into the ocean, its wreckage scattered across the seafloor. The search for the black boxes stretched on for nearly 2 years, finally answering what had happened in those final moments. Investigators from the French BEA found that the pitot tubes, critical for measuring airspeed, had succumbed to a rare icing event, triggering a cascade of automation failures. The crew's training had not prepared them for a high-altitude stall, nor for the subtle cues of unreliable airspeed. The final report from the BEA called for urgent action: redesign the pitot probes, overhaul pilot training on upset recovery, and clarify procedures for handling automation disconnects at crews. In the aftermath, airlines worldwide replaced vulnerable sensors and rewrote simulator curricula. The International Civil Aviation Organization issued new guidelines, making upset recovery drills mandatory for commercial pilots. Air France Flight 447 exposed the hidden risk of automation confusion and sensor failure at altitude, a lesson now etched into every pilot's training and every modern jet's design. Number 3. Japan Airlines Flight 123 reveals how one overlooked repair can echo across decades. On August 12, 1985, a Boeing 747 lifted off from Tokyo, bound for Osaka, carrying 524 people. Just 12 minutes into the flight, a deafening rupture tore through the rear of the cabin. The aft pressure bulkhead, repaired 7 years earlier after a tail strike, had failed catastrophically. Investigators would later discover a single-row splice, instead of the required double row, hidden deep inside the structure. With a sudden loss of cabin pressure, the vertical stabilizer sheared away. All 3 hydraulic systems were severed in an instant. The crew, stripped of flight controls, resorted to the only option left: throttle control. For 32 agonizing minutes, the pilots fought to keep the crippled jet airborne, using only engine thrust to steer. The aircraft pitched and rolled, tracing wide, desperate loops over the mountains of central Japan. At 6:56 p.m., Flight 123 struck the wooded slopes of Mount Takamagahara. Only 4 souls survived. 520 lives were lost. The deadliest single aircraft accident in history. The crash site revealed the truth. Metallurgical analysis showed fatigue cracks radiating from the faulty repair, a silent flaw that had grown with every pressurization cycle since 1978. Maintenance records lacked proper engineering sign-off. There had been no non-destructive inspection to catch the hidden weakness. The Japan Transport Safety Board's final report called for sweeping changes: strict adherence to manufacturer repair manuals, mandatory double-row splices, and recurrent ultrasonic testing on all major structural repairs. Regulators worldwide followed suit, introducing damage tolerance standards and enhanced oversight for maintenance procedures. The legacy of Flight 123 is written into every maintenance hangar, a reminder that in aviation, the smallest oversight can have the gravest cost. Number 2, United Airlines Flight 232 turned a routine summer flight into a crucible of survival and engineering reckoning. On July 19, 1989, a DC-10 bound for Chicago lost its number 2 engine at 37,000 feet. The titanium fan disc, weakened by a hidden manufacturing flaw, shattered without warning. Shrapnel tore through the tail, slicing all 3 hydraulic lines in a single devastating moment. The cockpit went silent. There were no controls and no response. Captain Al Haynes and his crew faced the unimaginable: a wide-body jet with 0 hydraulic power and 185 souls depending on them. With every control surface dead, the crew improvised. They used only the left engine and the right engine to steer, using throttle for pitch and asymmetric thrust for roll. Flight engineer Denny Fitch, a passenger that day, joined the cockpit and helped coordinate this desperate ballet. Sioux City Airport became their only hope. The approach was rough and the descent unstable. The DC-10 touched down fast, veered off the runway, broke apart, and erupted in flames. Yet against all odds, 111 people survived. The NTSB called it a miracle of airmanship, but the investigation did not stop at heroics. Metallurgical analysis traced the disaster to a microscopic crack in the fan disc, invisible to standard inspections. Regulators moved quickly. Ultrasonic testing intervals were slashed, and new containment rings became mandatory for high-energy engine parts. Aircraft designers physically separated hydraulic lines, ensuring no single failure could cripple all controls. Simulator training now includes throttle-only landings, a direct legacy of Flight 232. Every modern jet that keeps flying after a system failure owes its redundancy to the lessons written in the wreckage at Sioux City. And finally, in first place, the Boeing 737 MAX crashes shattered the foundation of modern aviation's trust in technology and oversight. In late 2018, Lion Air Flight 610 plunged into the Java Sea just minutes after takeoff. Less than 5 months later, Ethiopian Airlines Flight 302 met the same fate outside Addis Ababa. Together, 346 lives were lost. The cause was buried deep in software, a system called MCAS, designed to push the nose down if the plane sensed it was climbing too steeply. MCAS relied on a single angle of attack sensor. When that sensor failed, MCAS triggered again and again, forcing the nose down despite desperate efforts from the crew. Neither flight manual nor training had prepared pilots for a system they did not even know existed. Cockpit voice recordings captured confusion and alarm. Pilots asked, "Why is it going down?" That question would haunt the industry. The aftermath was immediate and global. Within days, regulators grounded the entire 737 MAX fleet. Investigators from Indonesia, Ethiopia, and the United States uncovered a pattern. MCAS was omitted from pilot training, documentation was incomplete, and Boeing's push to keep the MAX certified as a minor variant led to critical oversight gaps. The FAA's delegation of certification authority to Boeing itself came under fire, exposing weaknesses in the regulatory process. Oversight failures were laid bare. The response rewrote the rules. MCAS was redesigned to use data from two sensors, activating only if both agree, and its authority to move the stabilizer was sharply limited. Pilots now undergo mandatory simulator training on MCAS failures. The FAA and EASA imposed rigorous new checks on software-driven systems and reasserted direct control over certification for critical safety features. The 737 MAX tragedy forced the industry to confront the dangers of hidden automation, single-point failures, and the cost of complacency. Every boarding pass since carries the legacy of those 346 lives, a reminder that safety in the sky is never finished. Across all 5 disasters, one fact stands out. Every major advance in aviation safety is written in the aftermath of tragedy. Catastrophe exposes hidden flaws, then forces change. Today's flights are shaped by these hard-won lessons. In air travel, progress is measured not by perfection, but by relentless adaptation.